Hi, my name is Shanice Abram, and this is my lab report on Faraday's Law, also known as the magnetic molasses experiment. The purpose of this lab was to investigate Faraday's Law by observing how magnets behave when falling through a conductive tube, and then comparing those observations to a computational model. When the magnet falls, it creates a changing magnetic flux through the tube. According to Faraday's Law, this induces an EMF which drives a current. By Lenz's law, the induced current creates a magnetic field that opposes the motion of the magnet. This equation shows that the induced EMF is proportional to the rate of change of magnetic flux. The negative sign represents Lenz's law, meaning the system resists the change, causing the current. We used aluminum foil tube with these dimensions and dropped a magnet bar through it while recording it with an iPhone. Here's the picture of the setup. We measured the time it took for the magnet to fall the tube over 5 trials. The average time was 1.304 seconds, which is much slower than free fall. Instead of accelerating downward like in free fall, the magnet quickly reaches a nearly constant velocity. This indicates that another force is opposing gravity. In my computational model, I treated the magnet as a point dipole and the tube as a stack of conductive rings. I calculated the magnetic field, the induced current in each ring, and the force acting on the magnet. To simplify the model, I assumed the rings don't interact and the material is uniform, air resistance is negligible, and the magnet behaves like an ideal dipole. Both the experimental and the model show that the magnet slows down and approaches a constant velocity. Even though it does not share the same rate, this agreement suggests that the model captures the key physics of electromagnetic induction. If the resistivity were close to zero, the induced current would become very large. This would create a much stronger opposing magnetic force, potentially slowing the magnet dramatically or even stopping it. If there were holes or slots that were cut into the tube, the current loops would be interrupted. This reduces the induced current, which weakens the opposing force, so the magnet would fall faster. Some sources of error could include timing inaccuracy, non-uniform thickness of the aluminum foil, and simplifications in the computational model. In conclusion, induced currents release a magnetic drag force that slows the magnet, and the computational model agrees well with the experimental observations. Thank you.